Hello, this is Guolong. Today, I would like to introduce you FLACK, a tool to automatically locate bugs for alloy models. Alloy is a modeling language that has been applied in many areas. For example, model and verify the security of the European Railway Management System, the Internet of Things, and the surgical robots. Alloy is declarative, which is very different from imperative programs like Java or C. In Alloy, the order of statement doesn't matter, and there is no control flow. However, same as imperative programs, developers would also introduce bugs when writing Alloy specification. So to ensure the correctness of Alloy models, developer usually writes assertions. And for those violated assertions, Alloy would provide some counterexamples to disprove the assertion. The developer would then inspect the counterexamples and try to fix the alloy model correspondingly. FLACK follows the same procedure and tries to automatically locate these errors. Given an alloy specification, FLACK first asks the alloy analyzer to produce counterexamples. FLACK would then use the PMAX set solver to generate instances that satisfy the properties specified in the assertion and most similar to the counterexamples. FLACK then compares those counterexamples and set instances and find the minimal differences between them. Finally, FLACK analyzes those differences to produce a ranked list of suspicious expressions. Now let me use an alloy model for a finite state machine to show how FLACK works. For this finite machine, we have the following requirements. First, there should be only one start state and one stop state. Second, there shouldn't be any transition goes into the start state, and there shouldn't be any transition that's going out from the stop state. Third, all the states are reachable from the start state, and the stop states should be reachable from all other states. We would then write these alloy models trying to satisfy all the requirements. However, we actually make a mistake at this expression. The expression says that if a state has no transition, then that state is a stop state. To ensure the correctness, we write the following assertion, saying that there should be no transition from the stop state. Then we have this check command to ask alloy analyzer to check for the correctness for this assertion. Alloy provides this counterexample when we run the check command. In this counterexample, we can see that for the stop state 3, there is an outgoing transition to state 1. This actually violates the assertion saying that there shouldn't be no transition from the stop state. So what FLACK wants to do is to automatically identify this transition. So what we do in FLACK is to generate an instance that satisfies the assertion, and when we compare the satisfying instance and the counterexample, we want the difference between these two to be only contains the state 3 to state 1. However, when we try to generate some satisfying instance in alloy, these two would be the instance that alloy randomly generated, and from which we can see are very different from the counterexample. So FLACK then converts the problem to a PMAX set problem, in which the alloy specification and the predicate are the hard constraints, and the counterexample is the soft constraints. And the PMAX set solver tries to find a solution that satisfies all the hard constraints and as many as possible the soft constraints. In our case, the solution would be an instance that satisfies the predicate and most similar to the soft constraints, which is the counterexample. So in these two, we can see that the difference between these two are state 3 to state 1. That's the minimal difference to make the counterexample a satisfying instance. Using this minimal difference between the counterexample and the satisfying instance, we can get the relations that are most related to the error. In this example, we actually get the transition and stop are the most related ones. Using the relation informations, we can then slice the whole model to find expressions that are most related to the bug. In this case, we actually get 2 expressions. FLACK then tries to rank those expressions by assigning a score to each of them. For example, for this expression, FLACK would instantiate with the different value, in this case, state 3, and collect all the sub-expressions with the instantiated value. In this case, for example, we would collect this state3.transition, which we would then evaluate them in the context of the counterexample and the satisfying instance. For example, this expression would evaluate to state 1 in the counterexample and an empty set in the satisfying instance. And for example, this state.transition equal to null would be evaluated to false in the counterexample and true in the satisfying instance. There would be also some expressions that would be evaluated to the same value in both counterexample and the satisfying instance. Based on the difference between their evaluated result in counterexample and the satisfying instance, we would calculate a score for each of these expressions, and we would then combine them to get a final score for the expression. In this case, we get a 1.58 for the expression. Using that technique, given this LOE specification, FLACK automatically generates a ranked list looks like this. And we can see that the buggy expression was ranked first in this ranking list. To evaluate FLACK, we conduct 3 experiments. We use the top K matrix to evaluate the fault localization quality. Top K means that the tool is able to put the buggy expression in the first key locations of the ranking list. The first experiment evaluates FLACK on 152 small LOE models. Those models contain 20 to 60 lines of code. FLACK is able to rank top 5 for 83% of those models using an average runtime of 0.2 seconds. We also evaluate FLACK on 5 large LOE models, which contains 200 to 1,500 lines of code. Those models are collected from theoretical robot model and some machine-generated models for some Java program repair problems. FLACK ranks top 5 for 3 of them, and the runtime for FLACK ranges from 2.3 seconds to 1265 seconds. The long runtime was mainly due to the huge expression for the machine-generated code. We also compare FLACK with the state-of-the-art, which is for LOE fault localization, which is LOE-FL. Both two have very similar top K performance, an average 2.4 for FLACK versus 3.1 for LOE-FL. However, FLACK runs much faster than LOE-FL. It's like 150 times faster with an average runtime of 0.3 seconds for FLACK versus 32.4 seconds for LOE-FL. Today, I introduced FLACK, an automatic fault localization tool for LOE models, and we are working on some future work to integrate the result of FLACK with some automatic LOE repair tools. And you can download the FLACK at this GitHub repo. We also have another work on automatic LOE repair. If you are interested, please come to listen. And it also can be downloaded in this GitHub repo. And thank you very much.
Hello, everyone. Welcome again to the session about fault localization. I'm here with 2 of the authors of the paper, Gulong and Hamid. And they are happy to take your questions, so please enter your questions in the chat. And while we wait for your questions, I think I can I can ask a question. So in your approach, the localization is based on the generation of instances that are similar to the counterexample. You have this process, if I understand correctly, the way it works. I wonder if there are faults that might be hard to localize because of limitations in the way these similar instances can be built. So I would like to know more about the interplay between the capability to build these instances and the capability to localize maybe certain kinds of faults.
Yeah, definitely. So for some of this, even in the paper, we also discuss this problem is that some of the errors maybe not be fully discovered by the counterexamples provided. For example, in the paper, we provide some examples about the some binary search tree that the counterexample will only capture some of the values that actually appears, but the error actually caused by the left and right node of that binary search tree. And if the counterexample fail to capture this kind of information, then FLACK could not help really, like that will mislead FLACK to localize to some other unrelated expressions. So that's the problem that we are trying to solve right now.
Okay, I see. I don't see for the moment questions in the chat, so I will ask another one that is about the performance. I see FLACK is kind of very fast in terms of the average speed. I wonder if there are cases that may require a relevant amount of time. So it is fast in average. I wonder if there are some, difficult cases in terms of the performance.
Oh yes, so like for the 153 examples we test, most of the time is from like under 2 seconds. And for the large LLM models we tested, like for example the Java, the Taco Java, like the Java program, the LLM model converted from the Taco project that convert some Java specifications to LLM models. For that one, it's like one of them takes a really long time for FLACK to finish. This is due to in that model, it contains a really, really large expression. That expression alone, it takes like 300 lines of code. So it's because it's a machine generated model, so it's not human readable. And so when you have such large expression, then FLACK has to decompose, to find each of the small components of that large expression, and you have to analyze each one of them. And then that's why it takes a really long time for it to finish. But for the human written ones, it's usually pretty fast.
Okay, I see. Good. Okay, still see no questions on the chat. Since we have some time, just another quick point that is more a link to I think to another of your papers, because I really had the impression while following your presentation that given the way the faults are localized, you are kind of close also to guess a possible fix, because you have this comparison, you isolate the element that is likely responsible of the fault. And then as far as I can see, I think you have also a paper about the repair of the models, I guess. Just wonder how you go from, what do you need to add in order to produce a fix once you localize the problem, if you can just anticipate something about your follow-up paper.
Yeah, so yeah, we are working on a repair paper that's based on the result, and as the same as you said, we are trying to use the different values and relations that helps to guide the search. So basically, instead of the random search, we have these values that and the relations that we will consider first, like that because they are most related to the error. So when we try to generate the fix, this will be the this will have higher priorities to to select from. Yeah.
Okay. I see. Good. Anyway, I think the presentation still has to happen for the paper about the repair, right?
Yeah.
Good. Still don't see questions, so I think if there is no question from the audience, I think we can close the Q&A session. We have just a few minutes. Let me remind about the breakout room. So if anyone from the audience would like to join the authors, there is the breakout room available. Or I see now a question in the chat from Eunsook. Interesting work. Some of the errors in alloy models tend to involve multiple constraints. Does your technique find mostly local errors, or can it also be used to detect more global errors?
So it actually really depends on the assertions that you use to specify your expected behavior of the model. So it can also check for the multiple constraints, but in the ranking list, it will rank each expression based on their suspicious score we calculated. So if the error actually contains multiple, lines or multiple constraints, so it will also output that in the ranking list. But still, the user will need to, go through more of them to check if they are all related to the error or not.
Okay. Good. So no other questions. Okay. So again, thanks to the authors for the presentation and for answering the questions, and thanks to the audience for attending. We have the breakout room opening in a couple of minutes, and also another paper coming paper presentation coming in 2 minutes. Thanks, everybody.
Thanks, Leonardo. And thanks all for participating in my presentation. Thank you.